We have with us today a new Apollo mission director, Captain Chester M. Lee, U.S. Navy, retired. He will be assisted in the briefing by his assistant, Colonel Thomas H. McMullen of the Air Force.
Ladies and gentlemen, it is our pleasure to be here to brief you on the Apollo 12 mission. I would like to start out by saying that since rollout and transfer to the pad on 8 September, the testing has proceeded satisfactorily. We completed our flight readiness test on in October. We have completed our hypergolic loading on Saturday, the 18th of October, with no problems. We are presently in the process of loading the RP-1 fuel, and this should be completed today. We will enter our countdown demonstration preps. We should begin the countdown demonstration on Friday, early Friday. We will have a T0 for the wet CDDT, that's with the propellants loaded, on 28 October, and recycle for the dry T0 24 hours later. The launch count will pick up on Saturday, 8 November, with a liftoff scheduled for 11:22 Eastern Standard Time on the 14th of November. One issue that has been of interest to everyone is the issue of the color TV on the LEM. We have qualified the color TV, and yesterday at the Cape we ran an EMI test with a color TV hooked into the LEM, the PLIS, and all communications and telemetry on in the LEM. We did run into a problem that has not been resolved. We had several large black streaks across the screen. Now, this problem could be caused by a power problem, ground power problem, but we are not certain. As a result of this, we are planning at the present time to load the black and white cameras, which have to be loaded in a Mesa tonight. We will continue to test the color TV with the LEM 7, which is now at the Cape, to see if we can resolve this problem. If we can resolve the problem, we do hope that perhaps after the CDDT, we may be able to put the color TV back in the Mesa on the LEM. However, I caution you at this time that the chances of having color TV are somewhat dimmer than they were prior to yesterday. May I have the first slide, please? On Apollo 12, our primary objectives are as stated. As you recall, on Apollo 11, our objective was to land and return men safely from the moon. Apollo 12 has somewhat different objectives, but an extension of this, shall I say. We do want to perform senological inspection, survey, and sampling in the Mare area. This is a different Mare area. On this mission, we will deploy the ALSEP, which is the Apollo Lunar Surface Experiment Package, which will be described in more detail by Colonel McMullen. We are very anxious on this mission to develop techniques for a point landing capability. As you are all well aware, later missions will take us to spots that require a pinpoint accuracy. We do hope to develop our techniques on this mission that will lead us to perhaps further development on the next mission, leading us to getting a capability of landing at some very tight, difficult spots. We want to continue to develop man's capability to work in the lunar environment, and on this mission, one of our objectives is to obtain photographs of candidate exploration sites. We call this bootstrap photography, and I'll show you a few more details on this later. Next slide, please. This gives you some detail on the vehicles that will be used. The launch vehicle is 507, the command module is number 108. service module is 108. We're using the LEM 6, SLAW 15, and our onboard software programs are Colossus 2C and Luminary 1B. We will launch from Complex 39A. That's the one that most of the launches have been conducted from. Our crew, as you well know, are Commander Conrad, CMP is Commander Gordon, and the LMP is Al Bean. Next slide, please. This is a picture of our 3 astronauts. Next slide, please. The organization, fundamentally the same as in the past. There have been a few changes, primarily the mission director, which you know. We have a new launch director in Walt Caprian. Jim McDivitt has taken over as the manager of the spacecraft program. Roy Godfrey has relieved Lee James as the launch vehicle manager. Next slide, please. Now, with regard to the Apollo 12 mission, our design rules are as stated here. We want to follow the Apollo 11 timeline as closely as possible, and the only modifications we agreed to make were in procedures and techniques which would help us improve our landing accuracy. Now, in this particular launch, we will have 2 days per month instead of 3. Our launch site is somewhat to the west. If we cannot go on the 14th, we have one opportunity on the 16th, and that will be for a backup site, number 5, which is slightly further to the west and slightly to the north, as indicated on the far slide. Site 2 is where Apollo 11 went. Site 7 is where we're targeting for, and Site 5 is our backup site. Next slide, please. Now, with regard to the major differences from Apollo 11. Launch azimuth on Apollo 11, we were permitted to go from 72 degrees to 108 degrees, which gives us a larger, wider window. On Apollo 12, we are limiting ourselves to 96 degrees, 72 to 96 degrees. This will reduce the window approximately 50 minutes. The basis here was we felt confident that we could go in this time. We feel that we can reduce some of the ground support economical savings without any reduction in safety. Let me emphasize that point. Without any reduction in safety to the astronauts. The trajectory on Apollo 11 was free return. Once we made the TLI, if we did not fire another engine, we could not fire into LOI, this would bring us back to Earth. On Apollo 12, we are going to do a hybrid burn, a hybrid trajectory. We will launch on a free return trajectory, and approximately 28 hours later, we'll make a course transfer that will put us into a position for the first LOI burn. The free return trajectory that we would have gone on would give us a percentile of about 1,850 miles. This slight burn of about 65 feet per second will bring us in to about 85 miles and permit us to do the LOI burn. Now, this hybrid return, we will have the capability to use a DIPS engine to return it safely to Earth if necessary. On the way to the moon, after we have conducted the hybrid burn, if for some reason we find that we want to return, we have an RCS capability about halfway to the moon to give us a free return trajectory. The free return trajectory does give us a saving in fuel. It does permit us to launch from the Pacific, a Pacific injection, I should say, and give us the proper lighting conditions at Site 7. On this mission, we will have what we call a soft undocking, versus on Apollo 11, we had the hard undocking. And essentially, this means that the probe will be extended from the spacecraft and LEM. The LEM will essentially be suspended, and then the latches will be released and softly uncouple. This, we felt, was worth considering, as I will go into later, to help us in our navigational accuracy. The EVA period will be different in that it will be longer. On Apollo 11, our EV period ran for 2 hours and 32 minutes, and let me note that this was from the time of hatch opening to hatch closing. On Apollo 12, each EVA period should run 3 hours and 30 minutes each, and this will be from depress of the cabin pressure to repress, not hatch opening. They'll get in and get the pressurization going again. That is a difference, and if the portable life support system, the consumables are in good enough shape, it is a possibility that this may be extended some minutes. EVA radius, as you'll recall, on Apollo 11, Neil actually went about 250 feet when he went back to the crater. On this mission, we hope that we will have a greater capability, and it will depend on the ops purge capability. That's the emergency supply system. Should he lose, or should they lose, the portable life support system for one reason or another. We allow 15 minutes to get back to the LEM, and we allow 15 minutes to get into the LEM and repressurize. We feel that with about 4 kilometers per hour walking, that the astronauts could go about a half a mile away. The lunar surface state time in this mission will be approximately 31.5 hours from landing to liftoff versus 21.6 hours on Apollo 11. The lunar orbit state time will be longer, 89 hours versus approximately 60 hours. And this is primarily because we want to take another day in lunar orbit after being on the lunar surface, coming up, rendezvousing. We will stay in lunar orbit for approximately another 24 hours to get the photographs that are so very important to our follow-on missions. On the experiments, which will be covered in more detail later, we had the early Apollo scientific experiment package, which carried 2 experiments. This one will carry 5 and will be described later. On photography, on this mission, we are going to conduct the multispectral terrain photography at the moon. We're using 4 Hasselblad cameras that are ganged. I think they're red, green, and blue filter plus an infrared filter. We're also using a 500 millimeter lens to help us get some accurate landing site data. Sleeping arrangements we hope will be a little bit better. As you recall, Neil and Buzz had a difficult time sleeping on a lunar surface. On this mission, Al and Pete will have a longer sleep period. They have come up with a hammock arrangement which we feel will help them get a good rest. Lunar surface TV, black and white. I've given you our current situation with color versus black and white on this mission. The ascent stage on the Apollo 11 mission, we allowed to remain in orbit. On this mission, because we were very anxious to get rid of orbital debris, our intention is to deorbit the ascent stage and impact it close to the seismograph that will be implanted. By close, within 30 kilometers, we'll be fine. On trans-Earth flight, we have a longer trans-Earth flight, primarily because of our additional lunar stay in the Delta V. Total mission time, 244.7 hours versus 195.3 hours, essentially a little over 10 days on this mission from liftoff to splashdown. Next slide, please. With regard to some specifics, in the November launch dates and the December launch dates, there are some slight differences, but let me run through quickly. On November the 14th, you do have these handouts, and perhaps we can save time. I won't need to go through the others. Launch time on the 14th, the window runs from 11:22 to 2:28 p.m. or 1428 hours Eastern Standard Time. The free return trajectory that I mentioned would give us a percentian of 1,850 nautical miles. If we went on the 16th, it would be 1,000. And excuse me, let me jump up and show you that the window on the 16th, should we have to go on the 16th, will be from 14:09 hours to 17:27, 5:27 p.m. on the 16th. And I guess I would like to point out one thing on the December 15th launch. If we should, for some reason, get launch on this date, please note that 1847, this will be a nighttime launch. Getting back to the November 14th launch, the hybrid transfer delta V is 65 feet per second versus 40 on the 16th. Translunar times are essentially the same. The lunar orbit inclination on the 14th will be 15 degrees, 15.3 degrees versus 5.3 degrees. This has to do with Site 7 versus Site 5. The approach azimuth at landing is minus 75. In other words, we'll be coming up from south to north across the moon equator. The sun elevation at landing on the 14th is just about what we're after, 5.1 to 8.3 degrees, covering the full window. On the 16th, it's a little higher, 11 to 14 degrees. 14 degrees, we're getting toward the edge that we do not really like. Lunar surface time I've covered, 31.5 hours. Now, the sites that we'd like to cover in the bootstrap photography are Fromauer, Descartes, and Lalande. These are three sites that we are looking at for future missions. We have very little accurate photography, and we do want to pick up the photography on this mission. The total lunar stay time orbit is 89 hours. We'll do 45 revs. That holds for the 16th. Our trans-Earth flight time varies from 70 to 64 hours. This depends a lot on when we get off, and it's slightly longer on November the 16th. And again, our total mission time will run from 245 hours to 240 hours. Next slide, please. The nominal launch profile is as we had on Apollo 11. I won't go into too much detail. We have our max Q, center engine cutoff, outboard engine cutoff, S2 ignition, after the aft interstage jettison and jettisoning the LET, the launch escape tower, and the S2 engine cutoff, S4B ignition, and insertion at approximately 102, 103 miles nautical miles orbit. Total burn to that should be a little over 11 minutes. Next slide, please. You can take off that slide, too. I think there's another one that should come on this one. You want me to hit the launch board area first? On the right-hand screen, we have depicted here the launch abort areas. I wanted to point out primarily to show you that we can, by early staging and going to the S4B, get into orbit. So our concern, not concern, but the area where we would not get into orbit occurs in these first few minutes. I won't go into any more detail. If you have questions, we can go into it later. Now, with regard to the Apollo 12 flight profile, this again is quite similar to Apollo 11. We have launch, insertion, a 100 nautical mile Earth parking orbit. We have two opportunities for the translunar injection. We can do it on the second or third orbit. We will go into a free return trajectory. After this burn, we will have the spacecraft separation, transposition, docking, and ejection. Following this, the S4B will have an apse evasive maneuver to primarily to avoid any possible impact with the command module. Once we have completed this, we will have a residual propellant dump, and with another APS-Ullage burn called a slingshot maneuver to get us into a solar orbit. At approximately 28 hours after liftoff, we plan on a hybrid trajectory transfer. This will put us into then a position for the first lunar orbit insertion burn, which gives us a 60 by 170 nautical mile elliptical orbit. A second burn will put us into a 56 by 66 nautical mile orbit. Following this, we will have a ingress into the LEM and an inspection by the commander and the LMP. They will get back in. We will remain in orbit and get in position to do the DOI burn, separating the, and then we do the DOI burn first, right? Then separate after. No. Separate first and then a DOI burn. Provided everything goes well, we will then begin the power descent initiation, quite similar to Apollo 11, which is approximately a 12-minute burn to landing. After 31.5 hours on the surface, we will make preparations for the LEM ascent. We will then go into a LEM insertion, giving us an orbit of 9 by 45 nautical miles. We will then go into the co-elliptic burn and the constant delta height burns, bringing us up in phase and proper position with the command module. There will follow some braking maneuvers and then the docking. After docking, we will then do the additional 24 hours in lunar orbit to get the bootstrap photography. The trans-Earth burn will be as on Apollo 11. It will occur behind the moon and bring us a return to Earth with re-entry into Pacific as occurred on Apollo 11. Next. Let me just briefly point out that on this chart you can see what some of the times are, Eastern Standard Time, of some of the key events that will occur. I guess I can't help but note that some of these, the descent orbit insertion, the power descent, are again occurring at the wee hours of the morning. I will also point out that this is Eastern Standard Time, and Houston time this would still be on the 18th, but very close to midnight. Our landing will be early morning of the 19th. Our EVA activities will again be in the wee hours of the morning. Sorry, but that's the way it works out. Now, as far as translunar injection and ignition positions, I merely want to point out here that if we do not get off precisely on time, our launch azimuth will change. And we have the limits of 72 to 96, as I indicated earlier. If we launch at 72, the ignition of burn would occur in this position, cut off in this position. If we should move to some intermediate position, the burn will occur along this line of the trajectory and cut off at this line. So the burns will occur after our final check. This gives us a chance at Carnarvon to make sure that everything is go. Next slide, please. With regard to the hybrid burn, I would like to report out here that the spacecraft does not depart from a free return until backup propulsion that's the LEM dips capability is obtained. This is a safety feature. Again, I mentioned this previously. We can call on the dips engine to give us the necessary delta V to put us back on a free return trajectory and bring them back to Earth, where we can bring them safely and re-enter and recover them. And this is constrained to be available until 10 hours after paraloon, and this is typically 10 to 15 hours. And I pointed out earlier again, within this, after we've done this burn, we have within the RCS a capability of free return 1/2 way to the moon should something develop in our systems after we've made the hybrid transfer burn. Next time. For your information of what will occur, again, the same events I've been discussing. LOI 1 is the beginning of Rev 1. This is the ground elapsed time. I won't go into those. You have this handout. LOI 2 follows 2 revolutions later. We have the ingress into the LEM for housekeeping activities just as was done on previous missions. We will do landmark tracking for navigational purposes on 4, inertial attitude, and then back into the command module to begin a rest period and preparations, final preparations for ingress to the LEM checkout before we do landing site landmark tracking. Incidentally, this will be done from the command module with our undocking occurring on Rev 13 and the final landing occurring on Rev 14. Next slide, please. Now, with regard to the guidelines that I stressed earlier, that we would permit only changes in procedures and techniques to improve the navigational accuracy, let me point out what some of these are. Water and waste dumps will be avoided 8 to 10 hours before landing. We felt this imparted some delta V that was not accounted for and contributed to the large area that we had. In checking out the LEM, to avoid translational delta Vs, the LEM RCS checkout will be done with rotational maneuvers, just rotating the LEM, and with cold fire instead of null translational maneuvers. This then should avoid, we hope, putting some translational velocities to create a greater area that are not accounted for in our program on the landing site. The CSM in this case will do the undocking maneuver. Any delta V imposed, they will take. The LEM undock will be done radially to avoid downrange delta V. In other words, radially toward the lunar surface, they will separate toward the moon so we do not introduce any translational velocities. As I mentioned previously, soft undocking will be performed. Now, on Apollo 11, you'll recall that Mike Collins spent some time in inspecting the landing gear. And there was a lot of station keeping. And both of them ended up doing station keeping. This, we feel, introduced again some unaccounted for delta Vs. By nominal, we mean if the indications indicate in the spacecraft that the landing gear is down and locked, the inspection that Dick Gordon will make will be nominal. He will not go through all the maneuvers. And the CSM in this instance will be active in station keeping and not the LEM. Apollo 11, the LEM was active. This again is to reduce all motions in the LEM that are not required. And the CSM will perform separation. Now, under evaluation, still being considered, is the CSM LEM docked attitude maneuvers done using coupled thrusters to avoid any translational delta V. What essentially this means is that when we do any of these attitude maneuvers, we would like them to do with thrusters that are opposed so we don't introduce a delta V. Now, there is a problem on this. On Apollo 11, one thruster was not used because of plume impingement. And we have not resolved this problem. Specifically, we're looking at plume impingement on the high-gain S-band antenna to see if that antenna can take a plume impingement, and if it can, the chances are that we will do coupled thrusting to avoid this problem. Next. Now, additional items. On the LEM update, we will use additional LEM state vectors, and landing site vectors will be sent up to the computer on the landing path. We did not do this on 11. And let me just point this one, I'll move to the other chart. we will use landing pass misfin data to update the landing site relative to the LEM in the downtrack position. Essentially, what we're driving at here is that on Apollo 11, the LEM position and velocity and landing site position were sent to the LGC on pass 13, and these were based on data collected over 2 revs. We got 2 revs of data. This was run through the processor, checked, and then sent up on pass 13. And that was a final update before the landing. On Apollo 12, we're going to send up the landing site information in the state vector after 1 pass. We'll send it up on 13, and we will also on pass 14. And pass 14 is where they're coming around. They have separated, and that's just before DOI has been committed, and we're coming around to start the PDI. In this instance, as soon as we get AOS, as soon as we have obtained tracking in the data, they will quickly get some data. They will take care of the residuals that have been left in after the DOI burn and give a new RLS and state vector update to the LEM. Now, in addition, starting at PDI minus 4 minutes, we will do some tracking and use that information to update at PDI plus 2 minutes. That's 2 minutes after the descent burn has started. We will update a down track correction, downrange, to take out any errors that we have determined that would, say, make them land along their trajectory. These are the changes that we think will give us a much greater accuracy on Apollo 12 than we had on 11. Next slide, please. Here again, this is a picture, and I believe it was a lunar orbiter picture, of the landing site, and the surveyors right in that vicinity. This chart on the right, I think, gives you a better understanding of some of the difficulties in landing. You see we have the 99% probability curve running approximately 4,000 feet radii, and we have a 1 kilometer radius circle that we're targeting for. Please note that the circles, based on the photography we have, are reject areas. We don't want to land in that area. The present intention is that the surveyor is landing at this position in this crater. And let me point out one other thing. The circles drawn around the crater are not the actual crater sizes, but they've actually been enlarged to take care of the large boulders that we find on the edge of these craters. And I would like to also point out that this is a normal latitude. Note that north is not directly up. It's at a slight angle here, 15 degrees, and this is the approach path coming in. This is the target point. Next slide, please. This depicts the events that I mentioned, the DOI burn, command module remaining in the 60 nautical mile orbit, with the LEM starting its descent to the 50,000 foot point with the state vector and RLS update, coming down and starting the PDI burn at approximately 50,000 feet. An RLS update, that's the downrange update, at 2 minutes after start of PDI with a landing at this point. Next slide. These are some of the events in the final sequence here. I wanted to show this to give you a pictorial view of the LEM at these different points. The Ullage point, we're still some distance away from the landing. The power descent initiation is beginning at this point. The throttle to the fixed throttle position begins somewhat later, and note that, again, they are face up. They will not be face down at the beginning of this burn as they were on Apollo 11. In other words, you'll recall that on Apollo 11, at the beginning of the power descent, Neil Armstrong and Buzz were able to see some of the lunar terrain. In this case, the astronauts will be on their backs and they will not see this. And this is primarily for the landing radar. The landing radar, this is a position. They're starting to come up vertically slightly to get the landing radar in. At this position, we have throttle recovery. At F here, we have the landing radar velocity update. And at G, at this point, we're reaching 7,600 feet, or essentially high gate. And over on this chart, we have given you some of the times and the delta V's, or the velocity, excuse me, with the H dot that you will see. I think you will find this most interesting. As you'll recall, on Apollo 11, we heard some interesting information coming down from Buzz, who was reading the H dot. And I would like to point out the velocity here, we start power descent at 5,560 feet per second. You can see we're cutting down this velocity with the retrograde burn. The velocity of the H dot, that's a decrease in altitude, is slight here, but note that it does increase. And as he gets to the horizon visibility stage, he's at approximately 20,000 feet altitude. He's slowed, his H dot is fairly high. At high gate, he's starting to reduce, and you can see at low gate where essentially he is taking over manually, he's down to 14, 16 feet per second, around that, approximately 500 feet above the surface. Next slide. On the right, and please don't take this too literally, this is a picture of what Pete and Al should see coming into the lunar surface. This is taken from the LEM trainer. It was made up from the photographs. And you see, essentially, as I recall, we are at low gate. One of the points they're going to use, and I'm not sure I can point this out, correct me if I'm wrong, Bob, but isn't this the snowman here? One of the marks that they're looking for, and I believe this is right, you can just about make it out, is what they call a snowman. You see the body of the snowman with the two ears, and then his feet are here. The surveyor is in this spot. Is this one the big one? I'm sorry. Then here are your feet, and then these must be the ears. Just to give you an idea of what they're looking for and the problems they have of picking this out. I'm sorry I missed on picking out the snowman. I hope Pete doesn't have that problem. I've just been told that I was right the first time, so you can imagine the problems Pete's going to have. This is where the surveyor is. These are the feet, and these are the ears. There's your snowman in this area. Surveyor is in this spot. He's in the body. I think the crew did. I'm not sure. And that's at 4,000 feet altitude. What next one's what? Next slide, please. This shows you a little better. This is at 1,800, and I think I'm right on this one. The head, the ears, the body, and the feet. And this is at 1,800 feet.
The other way around.
This is it. Next slide. This is again, another picture. This is not exactly what they'll see. They will not see the surveyor. But this is essentially just before landing in the area. I think this is about where he could possibly get to, more likely in this area, depending on the lunar surface conditions. But that is, again, a picture from the LIM simulator giving you an idea approximately of what he should see. On the left-hand slide, I have a comparison here of that critical moment before landing to give you an idea of what was planned, what actually occurred as far as propellant monitoring for Apollo 11. And as far as events go, what we plan on Apollo 11, what actually occurred, and what is planned for Apollo 12. You all heard quite a bit about the low-level light sensor light coming on. This essentially comes on at approximately 2 minutes, slightly under 2 minutes, before complete, and let me emphasize, complete fuel depletion. On the Apollo 11 mission, ground control gave them a 60-second warning and a 30-second warning. At this point, you get a 2% gauge probability, which means you've got to commit. Now, when you reach that point, there should be 20 seconds of propellant remaining. And commit does not mean he has to abort. What ground control is telling them at that time is you must commit to either land or abort. And the 20 seconds of fuel remaining is to kill their vertical descent and to give them time to abort and then stage the ascent engine and have it build up the thrust and keep them clear of the lunar surface. Now, Neil Armstrong went about 40 seconds longer than the nominal plan. He actually had total fuel approximately 40% based on latest analysis, 40 seconds of fuel left. In other words, he was about 20 seconds before the commit point. After that point, he still had 20 seconds to prevent impacting lunar surface, staging, and getting clear. And I see we had planned, you see, landing with quite a bit left, and he went somewhat longer. Now, on this mission, as far as propellant notification goes, the procedure will be slightly different. The ground control will count up. Instead of counting down, they will count up. 30 seconds, 60 seconds, 90 seconds. 94 seconds will be his commit point. The landing, we hope, if things go nominally, and let me emphasize one thing, this is based on an automatic descent. When he takes over manually, that can vary, and he will take over manually at approximately 500 feet. But this is, we're about in this area, if everything goes right, this would be where we would expect him to land. However, we do anticipate that he'll probably use more, be picking out a spot to land. Next slide, please. Before Colonel McMullen takes over, just a couple of comments. The surveyor is on a 14-degree slope. It's about 50 meters, I understand, down the crater. The crater itself is about 600 feet across.